Just a reminder, today we have a term test, and the term test will be held in 2 rooms. So if your family name starts from Adams and ends with Khatib, you'll be in room 101. Kim to Zoe, building T13. Your room will be in 123. You all know where T13 is? Yes or no? Yes. Okay, so it's by Main Street West, beside ETB building. Is this like single-story bungalow or containers? Okay, so that's where our lecture is. Right. So today we're going to start on a new topic, and the new topic is due to normal stresses induced by bending moment. Okay, so there are different conditions of bending moment. So what are they? So we have centric, symmetrical bending, bending. Then we have eccentric, symmetrical bending. And then we have centric, unsymmetrical bending. And then we have eccentric, unsymmetrical bending. Okay. Now, whether it is centric or eccentric, what defines whether is it eccentric or eccentric? Anyone? Yes. Yep. So when it's centric, now have to be careful down here relative to bending. Okay. So in centric bending or in centric bending, there is no axial loading. Okay. So just to give an example of centric bending, okay, so we have a structure. This is our X, our Y rotation of Z. We have a pin, and we have a roller over here, and we have a load P over here. Okay. So for this case, okay, and then we have from here to here. Now for this case is what we call centric symmetrical. Let's handle centric bending first. Okay? Centric bending. Okay, this is what we call we call it as our centric bending. So if we look at eccentric bending, there is a axial loading component together with bending moment. Okay. So I'll do another different example. So now again, this is our X, this is our Y, this is our rotation about Z. Now it's a cantilever beam. Now in our cantilever beam, we have a load now, and this load, okay, over here has a applied force P. Okay, so P at that end will have two components. Okay, P at that end will have two components. We will have a what? Px, and we have a Py. Okay. So over here, this is what we classify as eccentric bending. Okay. This is what we classify as eccentric bending. And this is our distance from here to here, L. So for centric bending, what we tend to have is stress X is equal to moment about Z-axis over IZZ multiplied by Y. Okay. What is missing down here, anyone? You all learned this in 2P, right? But what is missing now? Yes. Yes, there's a minus sign down here. Okay. Why is there a minus sign there? Yes. Negative moment will cause compression. You're not wrong. Okay, but how many of you know what is a negative moment? Wait, negative moment. See, you cannot remember, right? I like Evans. Evans is like me. Cannot remember things well. I like that. There you go. Okay, Evans, I don't mean to embarrass you, but we can't remember. Right? But if you're in industry now, and there's no electricity, no network, right? And then you go for a job interview and require you to solve this. Can you Google it? And says no. So what are you going to do? Call me? No wire network. You can't call me. I will teach you a simple way to remember this. And it's all based on what? Visualizations of staring. It's all based on what? Visualization. Okay? What do I mean by visualization? Watch this. I'm going to draw the deformation pattern. Okay, so based on the centric bending, is the deformation pattern smiling face or sad face? Smiling face or sad face? The one on top, centric bending. Smiling face. How will the moment look like? It will look like this, yes or no? This is how the moment will look like. And experiments are meant to be what? Cheap. That's what. What's the difference between cheap and thrifty? Sorry, engineers are thrifty. What's the difference? I know tonight is term test, you don't need to hear this shit from me, but what's the difference between cheap and thrifty? Cheap means what? I like your calculator. Wait, I like your calculator. I don't pay a single cent. Why is that? Cheap. Thrifty means what? I like your calculator. How much you got for? $3? $1.50. That's being thrifty. Are we clear? So for this case, watch how my fingers are curling. My fingers are going to curl which way? This way, right? Take your ruler and curl this way. What will happen? Can you see the action? Yes or no? Okay? Don't memorize. Listen, when I teach this course, I take the textbook, I threw it away. Okay? It's all based on my analysis. Are we clear? You can remember. Okay? Right. So now when you see this, you have what? So always remember this. The only thing you have to remember now, at the head of the moment vector is always in what? Compression. The tail end is in what? Tension. That's all you need to what? Remember. Repeat again. The head of the compression vector is the head is of the compression vector is compression, and the tail end is what? Tensile. Now, why did they put a minus down here? If you were to look at the transformation, if we were to focus on the transformation, this is X, this is Y, this is what? Rotation about Z. If you look at the right-hand side, okay, if you look at the right-hand side of the center, okay, if you look at the right-hand side, the moment is what? Positive, right? So this is positive, moment about Z. Why? Because it's at the top of the structure is also what? Positive. But we know at the top, the structure has to be in what? Compression, yes or no? That's why they have to put the what? The minus sign. That is the only reason. But how I'm teaching you now is what? Don't worry about the plus, minus. Watch for the what? What to watch for? Deformation what? Pattern. Are we clear? Very important. Watch for the deformation pattern. And more important, the head of the moment vector. I'll write down here. Okay. Head of the moment vector. Note. The head of the moment vector is in what? Compression. And the tail end will be in what? Tensile. We clear? Okay. So that is for centric bending. Eccentric bending, right? We have stress X. Now this is equal to what? Px over A plus minus mz over izz multiplied by what? Multiplied by y. Okay. Again, I will put down here plus minus. Okay. Now, I want you to finish copying first, and I want you to look at two things. Okay. So if I have a point over here known as alpha, and I have a point over here known as beta, right? So stress X out. So before we go on, right, we know over here, this is under what? Px over A is under what? Axial what? Loading. And this is due to what? This is due to bending moment. So if we want, so now, how will the structure deform now? Axial, you can't see much, right? In terms of bending, it's going to deform this way. So in terms of bending, it's going to deform this way. That is our deformation pattern. And then this is how our structure will bend. The head is in compression. The tail end is in what? Tensile. So now, if I were to ask you to write stress X at point alpha, what is this equal to? Px over A, is it positive or negative? Positive. Bending moment, is it positive or negative? Look at the bending moment vector. I only have one person active learning. The rest are so quiet. So at alpha, the moment is it, so if I were to draw here, right, this is moment about Z, this is in tensile, this is in compression. What will you say about the bending moment alpha? Positive or negative? Evans? "50-50. You want to call a friend, you cheeky sort. And then now we have stress X at point beta. Px over A, is it positive or negative? Bending moment? Are we clear? You just need to stare at how the structure is what? Formed. Are we clear? Much quicker that way, much easier to see, okay? Because later on, trust me, I've done 3D structures, compound loading, okay? You have to use this. You don't use